power system blackouts represent the ultimate failure of a nation's electrical infrastructure, occurring when the balance between generation and demand is catastrophically lost. This analysis explores the causes, international experiences, and modern prevention strategies required to maintain grid resilience in an era of rapid energy transition. A blackout is defined as the total loss of power to a specific geographic area, often involving the disconnection of thousands of megawatts of load from the grid's generators. Unlike local outages, blackouts are frequently characterized by wide area disturbances and system separations where the high-voltage transmission grid is forced out of service. These events rarely happen instantly but rather develop through a series of complex events and technical failures that cascade across interconnected regions. The societal importance of electricity cannot be overstated, as modern life is fundamentally dependent on an uninterrupted supply for water purification, food preservation, and communication. Economic losses from blackouts are massive, leading to industrial shutdowns, the failure of hospital life support systems, and the total paralysis of transportation networks. Beyond economics, prolonged outages pose a significant threat to national security and public safety, especially during extreme weather or political instability. The anatomy of an electrical grid involves a delicate coordination between generation, transmission, and distribution systems managed by control centers using SCADA and EMS technologies. Historically, the evolution of blackouts has shifted from simple mechanical failures in the 1960s to complex, market-driven, and renewable integrated crises seen in the 2021 Texas storm and the 2025 Iberian collapse. These events are classified based on their origin, including natural, technical, human, cyber, or market-induced factors, each requiring unique defensive responses. The major causes of grid failure typically begin with initiating disturbances such as equipment failure, weather events, or operator error. Empirical data from Europe suggests that weather is the most common initiator, responsible for over 30% of serious events, while grid instability remains the most damaging in terms of total power loss. Blackout development follows a specific progression from a normal state through a disturbance to the redistribution of power flows, which may eventually lead to a total collapse. Cascading failure theory explains how the sequential tripping of one component, often due to thermal overload or voltage decline, places unbearable stress on remaining elements. This chain reaction causes the system to separate into isolated islands, most of which lack sufficient generation to remain active. Maintaining the supply-demand balance is a continuous physical requirement where grid frequency, typically 50 or 60 Hz, serves as the primary indicator of system health. Frequency stability refers to the grid's ability to maintain this set point. A sudden loss of generation causes frequency to drop, potentially triggering automatic load shedding as a final defense. Voltage stability, however, is often a more critical indicator of system stress than frequency, as it depends on the availability of reactive power VR. When lines trip, the remaining grid consumes more reactive power, leading to a rapid voltage collapse if local VR support from capacitors, statcoms, or synchronous condensers is insufficient. The thermal limits of transmission lines also play a role. High demand or ambient heat causes conductors to sag, potentially resulting in tree contact and further tripping. Modern protection systems, such as distance and out-of-step relays, are designed to isolate faults but can sometimes accelerate a blackout through protection malfunctions or hidden failures. The loss of system inertia is a growing concern, as conventional rotating machines are replaced by inverter-based resources IBR like solar and wind, which do not naturally provide the same resistive force against frequency changes. This transition creates renewable energy challenges, including converter-driven instabilities and a lack of traditional frequency support. If the grid does collapse, the restoration process begins with black start units, typically hydro or gas turbines that can restart without external power to re-energize the system. Operators must then carefully synchronize islands and pick up load in small increments while managing voltage and frequency control in a weakened, soft grid environment. Major historical blackouts provide invaluable data for improving international grid standards, with every event offering unique lessons in resilience. The 1965 Northeast blackout affected 30 million people due to a single relay malfunction, highlighting the danger of operating heavy loads without sufficient spinning reserves. The 1977 New York blackout was triggered by lightning and is remembered for its severe social impacts, including widespread looting and infrastructure failure. In 2003, a localized event in Ohio escalated into a massive crisis affecting 50 million people because of software alarm failures and poor situational awareness, leading to the creation of mandatory, enforceable NERC standards. The 2012 India blackout was the largest in history by population, affecting 620 million people. This collapse was initiated by the trip of the 400 kV Bina-Gwalior-Agra line due to load encroachment and a lack of reactive power compensation. When the line tripped, power rerouted through longer paths, increasing the transfer reactance and causing machines to fall out of synchronism, which manifested as violent power swings. The lessons from India emphasized the need for wide area monitoring systems (WAMS) and improved operator coordination across regional boundaries. The 2021 Texas blackout demonstrated the vulnerability of integrated energy systems to extreme weather. A severe winter storm caused frozen natural gas infrastructure and a massive surge in demand. This event underscored the critical need for weatherization and the maintenance of adequate reserve margins during climate-driven extremes. The 2025 Iberian blackout serves as a modern case study of how voltage instability and complex oscillations can rapidly collapse a sophisticated, high-renewable grid. The incident was preceded by a rapid, uncontrolled rise in system voltage and a total loss of voltage control in Spain. Technical investigations identified two distinct oscillatory episodes: 0.63 Hz forced oscillation and a subsequent 0.2 Hz inter-area oscillation. These oscillations were compounded by the fact that renewable energy sources residential were operating in fixed power factor mode, meaning they could not provide dynamic reactive power support to counteract the voltage rise. A critical factor was the mismatch in reactive power provision, where several conventional generators failed to meet their required Q reference targets. The root cause tree revealed that as voltage rose, generators tripped prematurely due to divergent protection settings, further reducing the system's ability to absorb reactive power. This created a point of no return where the Iberian Peninsula lost synchronism with the rest of continental Europe. Despite the activation of system defense plans, the cascading disconnections occurred so quickly that manual intervention was impossible. The role of inertia was also analyzed. However, simulations showed that even with higher inertia, the rapid loss of synchronizing torque would have still led to collapse. Weather-related blackouts are increasingly driven by the effects of climate change, with heat waves, wildfires, and ice storms placing grids under extreme physical stress. High wind gusts exceeding 80 km per hour have been shown to exponentially increase failure rates in transmission lines, often acting as the primary initiator for regional cascades. Human factors also play a decisive role. Operator decisions, the quality of SCADA interfaces, and the accuracy of alarm processing can determine whether a disturbance is contained or becomes a disaster. The 2006 European grid split is a prime example of how a single operational error can result in a continent-wide crisis affecting millions. In the modern era, cybersecurity has emerged as a distinct category of grid risk, with the potential for malware to disrupt communication or protection systems. Standards like IEC 62351 are designed to secure these digital assets, but the increasing complexity of grid automation provides a broader attack surface. The integration of telecommunications into grid operations means that a failure in public networks can severely delay restoration efforts, as seen when Spanish and Portuguese operators struggled with voice communication failures during the 2025 recovery phase. To prevent future collapses, grids must adopt smart grid technologies, including synchrophosors and PMUs, which provide real-time visibility into grid dynamics. Wide area monitoring systems (WAMS) allow for the early detection of the types of oscillations that destabilize the Iberian grid, enabling automated damping responses. Dynamic security assessment (DSA) tools are also essential, allowing operators to run continuous N-1 and N-2 contingency analyses to identify vulnerabilities before they are exploited by a disturbance. The concept of a self-healing grid utilizing automatic isolation and reconfiguration can minimize the impact of failures by preventing them from cascading into neighboring regions. Future grids will rely heavily on grid-forming converters and battery energy storage systems best to provide synthetic inertia and fast frequency response. Engineering recommendations include maintaining higher reactive reserves, standardizing protection settings, and improving operator training through realistic restoration simulations. Ultimately, the investigation of the 2025 blackout highlights that standardization across asset owners and the use of high-resolution telemetry are vital for ensuring the resilience of the global power system. Power system blackouts are among the most severe events that can affect modern electricity networks, often resulting from the interaction of multiple technical, operational, environmental, and human factors rather than a single failure. A disturbance such as a transmission line fault, generator trip, extreme weather event, equipment failure, or protection malfunction can initiate a sequence of events in which power flows are redistributed, transmission elements become overloaded, generators disconnect, system frequency or voltage deviates, and the disturbance propagates across interconnected networks. This process, known as cascading failure, can ultimately lead to system separation, widespread load shedding, voltage collapse, frequency collapse, and complete blackout. A critical aspect of blackout risk is the balance between generation and demand, which directly determines system frequency. Insufficient generation, loss of major generating units, low operating reserves, or reduced system inertia can cause rapid frequency decline and trigger under-frequency load shedding or generator protection actions. At the same time, voltage stability and reactive power availability are becoming increasingly important. A system may maintain acceptable bus voltages under normal conditions while having a very small voltage stability margin VSM to voltage collapse. Heavy power transfers, transmission constraints, inadequate reactive reserves, generator reactive power limits, and high penetration of inverter-based resources can significantly reduce this margin. Consequently, monitoring only voltage magnitude is insufficient. Operators increasingly need to assess the system's proximity to its stability limits. Preventing major blackouts therefore requires a transition from conventional static security assessment toward continuous, dynamic, and wide area assessment. Modern utilities and TSOs increasingly rely on phasor measurement units, wide area monitoring systems, energy management systems, dynamic security assessment, online contingency analysis, oscillation monitoring, and advanced voltage stability assessment. These technologies allow operators to identify abnormal system conditions before they develop into uncontrollable events. Adequate transmission capacity, reactive power reserves, synchronous condensers, STATCOMs, SVCs, FACs, HVDC systems, energy storage, and appropriate protection coordination are also essential components of system resilience. The future power system introduces additional challenges as conventional synchronous generation is progressively replaced or supplemented by solar PV, wind generation, battery energy storage, and other inverter-based resources. Reduced synchronous inertia, different fault current characteristics, complex control interactions, and changing reactive power behavior require new grid codes, protection philosophies, control strategies, and operational practices. Grid-forming converters, adaptive protection, AI-assisted security assessment, digital twins, automated corrective actions, and self-healing networks are therefore becoming important elements of future grid resilience. Ultimately, blackout prevention is not achieved by controlling a single parameter. It requires maintaining sufficient thermal capacity, voltage stability margin, reactive reserves, frequency reserves, inertia, protection security, situational awareness, and operational flexibility while considering credible contingencies and extreme events. The principal lesson from international blackout experience is that system resilience must be continuously assessed before, during, and after disturbances. A reliable future grid will depend on combining strong physical infrastructure with advanced monitoring, dynamic security assessment, intelligent protection, coordinated operator actions, and new control technologies capable of managing an increasingly complex and highly inverter-based power system.